Okay, I guess we can start. So we have looked at perturbation theory, and we have two important results. Okay, so remember we are still working with non-degenerate perturbation theory, and we have obtained two results for the shift in the energy. If I look at the shift in the energy level to first order, that actually was quite simple. We had this psi n0, the original state, times h1, okay, psi n0. So that's the expectation value of the perturbation in the unperturbed state. And if I look at the second order shift in the energy, that was in the form of a series, okay, which relates to energy levels. So I have this En 0 minus Ek 0. So quite obviously I cannot have K equal to N. And I have here expectation value of H between, doesn't really matter, K 0, H1, psi n0 magnitude squared. Okay, and we gave these things names, so let me just put it that way. It's just this H1 in the N matrix element. This is K not equal to N, E N0 minus E K0, and H doesn't matter really, NK or Kn, because they are just going to be magnitude squared anyway. Okay, so those are the results. I want to just work out some examples today. And the basic example that I'll work on is the harmonic oscillator, because it's easier to okay, so it's the perturbed harmonic oscillator. Okay, so we have our system, the unperturbed Hamiltonian, which looks something like this. Okay, so this is our v of x as a function of x, and this v of x is 1 over 2 k x squared. Okay, so I'll now put in various types of perturbations to it and look what happens to it in first order and second order perturbation theory. Now, the first thing we can do is, okay, let's just analyze this sort of conceptually, what's going on here. Suppose I add in an H1, okay, some additional potential, which looks something like alpha x. Okay, so this is a linear potential like this. Okay, so linear potentials like this you can usually implement by putting some electric field. If you have a charged particle, for example, inside this potential, then the field will generate a uniform field, will generate a linear potential. Okay, but what happens now? This is a problem which we can obviously solve exactly, right? Because this now becomes our potential v of x is now equal to 1 over 2 k x squared plus alpha x. But I can complete the square of this. So it's going to be 1 over 2 k x plus something squared, so that I get that alpha x. And what is that going to be? Well, if I choose that as alpha over k, will that do it? No, I think we're okay. But it will generate a square term, which I have to handle. So that is going to be minus 1 over 2, alpha squared over k, right? So that's equal to that. So it means that what I have here is still a parabolic potential, except that its zero reference has been shifted. So what I have here is now going to look like, let's draw a red curve. It's going to have a minimum at x equal to minus alpha over k, okay, some point over here. So it's going to be a potential with the same quadratic form. It's going to be tangential to this line over here, but do something like this. So its minimum is going to be somewhere over here, and it's going to be down, okay, by this factor 1 over 2 alpha squared over k, right? So all of the energies will shift by alpha squared over k. The 0 point of the oscillation will shift. Okay, it's just like, you know, these freshman problems when you have a mass and a spring, and you hang a mass from a spring from the ceiling. What happens? The problem really doesn't change, okay, because of the gravitational potential energy, which is again linear like this. You just get a different equilibrium point, but the stiffness of the spring, etc., they will all be the same. So we have something like that. So it's a lower potential, okay, and it just shifts. Everything will be shifted. So the ground state energy, whatever it is, it will also be shifted down by this amount. And you see, I am putting in a perturbation proportional to alpha x, and my shift in the energy is going to be proportional to alpha squared. So I expect to get nothing out of this in first order, but in second order, in principle, I should get the exact result, because there is no alpha cube or alpha 4 term that's generated by this. Okay, so that should be that. Okay, so let's do that. Let's just look at all of these things. Let's just clean up certain details. Let me just derive what this x0, etc. are. So the Hamiltonian is going to be equal to p squared over 2m plus 1 over 2 k x squared. So what we do is we divide this by h bar omega c, right? And we get p squared over 2m h bar omega c, so that we have a unitless quantity. So k over 2 h bar omega c x squared, okay? And then we said this I can write as an a plus and an a minus, right? So this is going to be, let me see, yeah, okay, so it's going to be one factor, so I just factor this out. I write this as some x over x0, a plus a minus, so it's minus I p over p0, and x over x0 plus I p over p0, right? That's the factorization. Then there's a plus by 1/2, which comes in because these things do not commute. And this thing we call a plus, and this thing we call a minus. So this x0, which divides this, is going to be, or x0 squared is going to be equal to 2 h bar omega c over k. Okay, so it's something I want to keep in mind. All right, so my h1 is equal to alpha times x, which is equal to alpha times, if I just add these things up, I'm going to get a plus plus a minus, okay? But I also need to multiply by x0 over 2, right? So that I get an x there. Okay, please check my algebra. All right, so that's our h to first order. And I now am going to look at the shift in the energy. Let's just say the ground state to keep things simple. So what is the shift of the energy of the ground state to first order? Well, I have the equation right there. Okay, so it's going to be the unperturbed energy states of the original Hamiltonian, 0, alpha x, which is our h1, 0. Okay, so that's going to be alpha x0 over 2, and I have 0, okay, ground state times a plus plus a minus and 0. And you can see that this is just going to give me 0 because a plus or a minus, they either raise or lower this thing by 1, and that is going to give me 0 from the inner product. Okay, so there is no linear, okay, first order change to the energy, okay? So I have to look at what happens in second order. So now I have to go to the second order. So let's do that over here. Well, maybe I'll keep that equation up there. So I'll go to second order here. So E0 to second order is now going to be equal to that equation. But you see, I'm going to only really a single sort of thing. Okay, let me just write this down. So it's going to be a k not equal to 0, okay, summation, divided by E0, okay, to 0th order minus Ek to 0th order. I'm just rewriting that equation, okay, except that I'm putting n equal to 0. And in the numerator, I have h0k magnitude squared. So h0k, when I look at this expression, h0k is 0, okay, alpha x and k, okay. Yeah, I should have written it the other way around, which in fact will make my discussion a little bit more transparent. Okay, one is the Hermitian adjoint of the other, so it doesn't really matter which way you do it. We are going to take the magnitude squared anyway. Okay, so you see this x is going to contain an a plus and an a minus. So the a minus doesn't help because a minus on the ground state always gives me 0, but a plus is going to give me, okay, 1. So the only term that is going to be finite here is going to be h01, which is going to be 1, okay, alpha x0 over 2, okay, a plus plus a minus. But this a minus is going to give me 0, and I have something like that. So a plus times, okay, 1 is going to give me, okay, so this just gives me alpha x0 over 2. A plus on 0 is 1, so it's going to 1, 1, which is 1. Okay, so it's going to be alpha x0 over 2. Okay, so what do I get? There's only k equal to 1 term here. So I am going to get this h01 magnitude squared divided by E0, which is h bar omega c, minus E1. Well, not really. This is 1/2 h bar omega c, right? Okay. 1/2 h bar omega c minus 3/2 h bar omega c. Okay, so you see this is negative. So this is something we talked about earlier. The other states, okay, in second order perturbation theory, whenever you have these states, other states tend to push the energy in the opposite direction. Okay, so in this case we have the ground state, okay, and over here 1, this state is pushing the ground state lower. Okay, so we are going to get a negative result. All right, so we are going to get minus h bar omega c, and in the numerator I am now going to get the square of this, which is going to be alpha squared x0 squared over 4. Okay, so x0 squared, I had written it somewhere over here, so let's put that in. So this is going to be alpha squared over 4, and x0 squared was 2 h bar omega c divided by k, and then I have minus h bar omega c here. So the omega c's will cancel, and I'm going to get minus alpha squared over 2k, right? And in fact, it's exactly what we have down there, okay, for the exact shift in the energy. So in this case, since the energy shift is exact and you have only terms up to second order, and then the mathematical expansion obviously just gives you that. So if you go to higher orders, even though we didn't discuss what you get in third order, etc., but you are not going to get anything, okay? You are going to get just zeros out of that. Okay, any question about this? Okay, another type of exact thing that you can do is you could add a quadratic perturbation to this, right? You have 1/2 kx squared, and you could add something like 1/2 qx squared. Okay, what does that do? That just stiffens the spring a little bit more, shifts the energies, okay? And you can, again, find the exact energy and see how it compares with the perturbation. Yes?
Does other states also, does E1 second order correction, is
Yes.
it 0 or is it the same?
No, okay, it's going to be the same. Why? You can see that the whole potential is just being shifted to a...
Intuitively, yes, but I did some calculation, but I'm finding 0.
You are finding 0?
Yes, because A plus plus A minus, these are both giving square root of n.
Okay.
And then when you do the calculation, one of them is above, one of them is low, so one of them gives plus, one of them gives minus, and they go to the same amount.
Well, shouldn't be, but since you asked the question, maybe we can...
When you do the calculation, it gives you square root of
Okay, well, okay, I was
I'm not sure what.
planning on going to the fourth order perturbation, but since you are asking that, let's just do that, okay? So let's just see what happens for the nth order, okay? So now what I want to look at is, okay, quite obviously, if I now look at the energy shift, okay, to first order in the nth state is going to be n alpha x n, and now again I have either a plus or a minus, so I'm going to get 0. Okay, so there's going to be no change to first order. Now, the second order, En2, let's see what that does. Well, the equation is over there, and we have seen that we need only the higher and the lower states. So there will be two contributions. Okay, so there will be an En0 minus En minus 1, 0, right? That's the lower energy level. And I'm going to get here an Hn n minus 1, okay, magnitude squared for the object. And then there will also be plus En0 En plus 1, 0, okay, and Hn n plus 1 magnitude squared. Okay, so those will be only surviving terms, right? Because this alpha x either raises by 1 or lowers by 1, so I get either n minus 1 or n plus 1. Okay, so let's see what these things are. So I am interested in finding, for example, Hn n minus 1. Let's just find that first. Okay, so suppose I have something like this, n, and then this is 1. I have alpha x0 over 2, a plus plus a minus, n minus 1, right? So what will this be? Alpha x0 over 2. Okay, so a minus will lower this, so I don't have to worry about that. So it's the a plus that I have to work with. And a plus is going to give me what?
Square root of n times.
Okay, square root of n, and then I have n. Okay, so that's that. Okay, let's look at what Hn n plus 1 is. That is going to be n alpha x0 over 2. And now I have again a plus plus a minus. Okay, and I have an n plus 1 here. So now what do I get?
Square root of n times alpha x naught over 2.
Okay, what do I get? Square root of n plus 1, right? Okay, so this is going to give me alpha x0 over 2 square root of n plus 1 times n plus 1 n plus 1. Okay, so I guess now you know where this is going to. Okay, so let's now put these things in. N and n minus 1. Okay, the common factors is going to be alpha squared x0 squared over 4. Okay, the square coming from both of these things. And then over here, I have En minus En minus 1. So I'm going to get a positive quantity, which is going to be h bar omega c. And n minus 1 is going to give me, okay, square of this, which is going to be n. And then the other one is going to be the other way around, minus h bar omega c. And but now if I do that, n plus 1, so very nicely, okay, the n parts cancel, and I end up with minus alpha squared x0 squared over 4 h bar omega c, which is what I had earlier. Okay, so it works out very nice. Okay, so let's look at a real perturbation which we cannot really handle any other way. Okay, so suppose I have this harmonic oscillator again. Let me keep some of the stuff over there, and let's see, in fact I'll erase this Phys over here also. Okay, so suppose this time I put in a fourth order, okay, object. So suppose I have h1 is equal to, let's put a different constant because this will have different units. So let's call it beta, okay, x to the 4. Okay, this is called an anharmonic oscillator, and the solution to it is not trivial, especially if beta is large. Then this, you get very interesting effects from this. Okay, but we'll assume, okay, the perturbation limit where beta is very small. So now I need certain matrix elements. Okay, so in order to calculate this, I'm going to need things which look like 0, h1, 0, right? So this is going to be the first order change, but the second order change and such things, I'll need 0, h1. Okay, let me put the 0 on the left, right again. Okay, things like that. Okay, so for some general k. So I need to find out, okay, so the best strategy perhaps is to find out what happens when h1 hits on the ground state, because it's going to generate some stuff. Okay, so I'm going to look at the problem of what happens when I hit on the ground state with h1. Okay, so that is going to give me beta x0 over 2 to the 4th power. Okay, because x, okay, I erased that, but it's equal to x0 over 2, a plus plus a minus. So I have a plus plus a minus operating the 4th power operating on the ground state. Okay, so it's just the problem of counting, okay, so that I don't get any zeros. Okay, so it's really some amount of algebra, but I'm confident that you'll help me. Okay, so I can have all a pluses. I shouldn't have any a minuses on the right. In fact, I shouldn't have more a minuses at any point than a pluses on the right, otherwise I get 0. Okay, so that's one possibility when I take the 4th power of this. I am also going to get things which look like, okay, so these are all a pluses, 1 a minus. Let's go systematically. So that's another possibility. Okay, a plus, a minus, a plus, a plus, a plus, a plus, a minus, a plus, and that's it. I cannot put a minus anymore to the right, right? Otherwise, if it's on the right, it's going to kill the ground state, which I don't want. And then I am going to look at 2 a minuses. Okay, a minus, a minus, a plus, a plus. I can move one of these guys towards the right. A minus, a plus, a minus, a plus. Right? Can I do anything else?
A plus, a minus, a plus.
Okay, that I cannot have, because if I have a plus, a minus, a plus, this will just bring it back to a 0 and this will kill it. Okay, so am I missing anything?
These must be it.
Okay, if a mathematician says so. Okay, we trust but we verify. Okay, that's trust but verify. That's how what people do with nuclear weapons. Actually, okay. Yes. Okay, so we treat mathematicians like nuclear powers. Okay, so we have this thing acting on all of these things acting on zeros. So help me out. What does this give me? So it goes up to 1, 2, 3, and 4, right? And I get 4. Okay, so this is again up to 1, up to 2, up to 3, and down from 3. Okay, so that's that. So that's going to be 2. Up from 1, up from 2, down to 2, and then what do I have here? 1, 2, 1. I think it's 1, right? Mm-hmm.
It goes to 1, it goes to 2.
Okay.
It should be 2.
Okay.
It's 1 and we applied up, it should be 2.
Okay, yes, okay. So, what about here? 1,
1, 1, 1, 2.
1, 1 again, and 2. Okay, root 2 again. And what else? These are now 2 plus and 2 minuses, so they are going to give me zeros. So this is going to give me 1, 2, 1, and 1. 1, 2, 2, no. 1, up to 2, down from 2, and 1, right? So this is 0. And finally, this is
1, 1, 1, 1.
Sounds tempting, but let's verify. 1, 1, yes, 1 and 1. Okay, so this object, a plus plus a minus, operating on the ground state, gives me 2 plus 1, 3 ground states to the 4th power, plus how many square root of 2's? There's 1 square root of 2 here, 2 over there, 3 over there. It looks like 6, right? Plus 6 square root of 2, 2. And I don't want to reduce that. That's just 4 factorial 4. Okay? So now it's time to apply the equations. Okay, now you see I get something even in the in the first order. So E0 in first order is going to be equal to this beta x0 over 2 to the 4th power, and I'm going to get 0 a plus plus a minus to the 4th power 0, and I just decided that that would give me 3. Okay, so that's, this whole thing is 3, and I end up with 3 beta x0 over 2 to the 4th power. Okay, and you can see that the units are okay, right? Because beta to the x to the fourth was our term that we added to the potential. And you get this interesting result that, okay, this x0, which is the typical length of oscillation in the object in the quantum oscillator, you just look at x0 over 2 to the fourth power and multiply it by beta. That gives you the first order object. Now, the second order, I have to be careful, okay, because that is going to generate a number of terms which go like that. So, what are the finite terms? There's going to be the k equal to 2 term. So, okay, let me first write them down. H 0, 2, okay, magnitude squared divided by E0 minus E2. But then I'm also going to get H04 squared over E0, 0 minus E2, 4. Oops, not really. E4, 0. All right. So, what are those things? Magnitude squareds of these things. So, it's going to be beta squared x0 over 2 to the 8th power. Right? So, that's going to be common. Beta squared x0 over 2 to the 8th power, which will factor out from both of these terms. And then I'm going to have a minus 2 h bar omega c energy difference here. And h0, 2 magnitude squared. So h0, 2 will pick out this term. Okay. When I take the inner product of that with 2, I'm going to get 6 square root of 2 squared. Then I have the other term, okay, which is going to be minus 4 h bar omega c. Okay, and h04 squared. So that's going to pick out that term. So it's going to be the square of 4 factorial. Okay, something like this. Okay, algebra time. So this is going to give me now beta squared x0 to the 8th over like 0 over 2 to the 8th power. Okay, there will be a, let me pull out a minus and an h bar omega c. Okay, so this is 2. Okay, so it's just 36, right? And then this one is, okay, it's just 6. Okay, so this will simplify a little bit. So what will that give me? It's going to give me beta squared. Okay, so this is 18 plus 3 is 21. So that's interesting because that says that this is going to be minus 1 over h bar omega c 21 in the denominator if I just take one of these 2's away. So 2 to the 7 is what?
128.
Okay. So that's what we have. And what happened to the x zeros? X0 to the 8. Okay, so we get this number. You see, you have growing powers of x zeros and things like that. What we are assuming when we are doing this perturbation theory, that these factors, okay, the physical factors, are less than the energy scale. So we are assuming that this beta squared x0 to the 8 divided by h bar omega c is much less than h bar omega c, okay, the energy levels, okay, at various places. So what that means, again, if you just divide by h bar omega c and obtain a square root, beta x0 to the 4th divided by 1 h bar omega c is still much less than 1. Okay, and that's the basic assumption, right? The h bar, the beta times x0 to the 4, okay, is the scale of h1, okay? So we have beta x, we assume is going to be of the order of x0, okay, typical length in this harmonic oscillator. So that thing multiplied by x0 over 4, we assume is going to be a small effect, so it's going to be less than h bar omega c. So this is really the smallness parameter in the problem. Okay, that's the lambda, okay, that we tried to introduce in the beginning. So if this is small, you see in second order you get the square of this, which is going to be even smaller, and so on. Okay, so that's good for convergence and such things. In any case, so this is what happens when we have the when we have the fourth order perturbation. Any questions? All right, so what else can we do? Well, we could do the similar thing for any problem, really, but typically people do this. We don't really have time to finish the problem for the infinite box. Okay, infinite 1D box. We can put a linear potential into that. So again, if I just take something like this, which extends from minus a over 2 to a over 2, and infinite potential over there and over there, I know what the ground state wave function is. u1x is going to be square root of 2 over a cosine just 1 pi over ax, right? So that's our ground state. Now, if I want to actually find a shift in the energy due to some perturbation, so again, let's just assume we just put in a linear perturbation. Okay. Now, when I put a linear perturbation, what happens? The potential turns into something like this. Okay, so that's our x, and we end up with a potential which looks like this. Okay, so this problem in one dimension does have an exact solution, okay, in terms of some special functions called Airy functions. And you can solve this problem using the Airy functions and get a result. But if you just use perturbation theory, in fact, to first order, you can immediately see that you are going to get 0, so you have to do the second order perturbation theory. But if you do the second order perturbation theory, you get something which is correct to 0.1%. Okay, it's an extremely effective approximation. In any case, how do you do it? Well, let's just start. The change in the ground state, or in fact any state, to first order is going to be, well, there's no zero in this problem. So the shift of the ground state energy is going to be, okay, 1 alpha x1, and that is going to be equal to 2 over a integral minus a over 2 to a over 2 x cosine squared, just 1 pi over a x dx. Okay, and you see that I have an even function here, okay, an odd function there, so I'm going to get 0. So the first order I get 0. Okay, so what happens under the effect of this perturbation, the wave function, instead of being symmetric, now if you look at the corrections to the wave function, it will now start to move towards the, okay, lower potential. Okay, so there will be contributions from higher order terms, and to find out what happens, I'll need elements which look like 1, okay, alpha x with the kth state. Now I can put in, okay, you see other cosines. Remember, because those are the even functions which correspond to odd numbers in the wave functions. As long as I put other even functions, if this is even, that is even, okay? If I have even function there, odd function in the middle, that's going to give me 0. So I need, if this is even, that's odd, I'll need odd functions. Okay, so this is going to be 0, okay, this is going to be a little confusing, but for k odd, okay, so if k is equal to 1, 3, 5, etc., then I get even functions, although the number is odd, functions are even. Okay, so these things correspond to, again, even functions. Okay, this is even function. So I need to find things which look like 1 alpha x k, okay, which am I doing the wrong? I'm writing the wrong thing here. This is 0 for odd functions, okay, even, odd, okay, this is odd. Okay, so this is not going to be 0 for k even. Okay, so in that case, this is going to be a sine function. It's going to be odd. This is going to be a cosine function. Okay, and this is just x. So I'm going to get terms which look like, okay, so that's going to be equal to 2 over a, okay, an integral from minus a over 2 to a over 2, cosine 1 pi x over a times sine, okay, k times pi x over a, and then there's an x dx, okay, and then alpha. Let's put the alpha over here. Okay, so that now is going to give us h1 1k. Okay, so obviously you have to do this integral, which is not really that bad, okay, but it will take some time, okay, but you can get what this result is, put it in the series, and you have a solution to the energy with an accuracy of 0.1%, which is very good. Okay, yes.
I noticed something interesting. If we were taking the Hamiltonian to be Hamiltonian of free particle in an unbounded domain, then a small perturbation will change our system from one with continuous spectrum to discrete spectrum.
Okay, so the whole idea behind this perturbation theory is that the system should not change very much, okay, not qualitatively, okay, when you do something like so. If that does happen, then there's something drastic happening to the system, and you can no longer call that a small perturbation, okay, so
it will be a bifurcation.
well, okay, so I don't know. I used to say certain things in the past, but now those things are not considered politically correct. Just skip them. Okay. Yeah, I'll see you in the exam, right? Friday.